Hi everyone and welcome to this lecture. Today we are going to see the geometrical interpretation of the gradient operation. You have already seen how to calculate gradient of a scalar function, and today we are just going to interpret what this gradient operation actually means in geometrical manner. So let's get started. So if you recall that the gradient operator was denoted with this nabla symbol, and it was expressed as the partial derivatives and the unit vectors of the coordinates. That is, it was expressed as this. Right? And if you have a scalar function, let's say scalar function is phi, so phi is a scalar function, or so to say a scalar field. So the gradient of phi would then look like this. And you have to keep in the back of your head that this phi can be a function of x, y and z. So this was the gradient operation, right? Now, what does this mean? That's the thing we want to figure out today. So, to interpret the gradient of a scalar field geometrically, what we're going to do is that we're going to consider a three-dimensional space. So, we're going to consider a 3D space. A familiar space is this x, y and z coordinate. And if you draw it like this, let's say this is our x, this is our y, and this is our z axis. And then we are going to consider a displacement, a small displacement in this 3D space. It's also known as the Cartesian 3D space. So this means if you have a vector like this, and let's say this is the initial position, and let's say this is the final position. And the difference between them is our displacement. And let's call this displacement as dr, and you can give an arrow to indicate that this is indeed a vector displacement. Okay, and inside this 3D space we are going to introduce some scalar field. So let's say the scalar field is over here in each and every point of this 3D space. So we have the scalar field phi, which is a function of x, y and z in this 3D space. And note that I'm not taking any explicit example. We can do it in general, so that's why I'm sticking to the most general notation. So now let's consider a quantity. So now consider a quantity, and this quantity will be the dot product of the gradient of the scalar field with the displacement vector. Also, this is a vector as well. You can give an arrow over this, and if you write this explicitly, then this will be just the gradient of the scalar field, that is these partial derivatives and all the unit vectors, and this dr, since this is a displacement in the x, y and z, we are going to introduce the scalar displacement, and we are going to associate the unit vectors to indicate in which direction this displacement is occurring. So this dr will be nothing but dx I hat dy z j hat and dz k hat, and there is a dot between them. That means you have to dot product these two things. So if you do that, that is after taking the dot product, this is just del x dx, del phi del y dy, and del phi dz, like this. But now this is something you are familiar with. If you recall that this is indeed the absolute derivative, or let's say the absolute differential of this scalar field phi. So this is just d phi, because if you have a function, let's say a function of x, y and z, d of f of x, y and z is just the partial derivatives and their small intervals displacements, or like this. And this df, this is called the absolute derivative, or let's say the absolute differential. So this is the formula that we have used on this line, or let's say an identity, whatever you want to call it. So our gradient of the scalar field dotted with the displacement on that 3D space is giving us the absolute differential of the scalar field itself. So let me just write it out again. Sorry. So what does this d phi mean, right? This d phi means an infinitesimal change in phi going from position r to r plus dr, because our displacement was dr. That is, if you look at this picture over here, if you go from this point to this point, the field itself will change like this, that is d phi. And this dot product can also be thought of as a projection. So gradient has something to do with the directional derivative, right? Because if you recall that a dot b, recall, if you had a vector like this a, and if you had a vector like this b, and they had an angle between them theta, then a dot b gave us modulus of a, modulus of b, and cosine theta between them, right? And this a cosine theta, that is these two terms, that is, this thing was nothing but a projection of a onto b, and here we have something similar. So this gradient has something to do with the directional derivative, that is in which way you are going, and the field is changing accordingly. So that's why I showed this thing to you first. So from here you can suspect that gradient has some relation with directional derivatives. Right? And now we are going to see how we can actually relate them. So what we're going to do now is that we're going to take the same 3D space, that is this x, y and z, and in this 3D space we are going to introduce a space curve, that is a curve that lies in this 3D space. So let me draw that first. So let's say this is the curve, something like this. So this is our curve, and this curve can be parameterized with some parameter as r of u. So let me explain that. What do I mean by this? So if you consider a vector from the origin to a point of the curve as a particle or someone moves along this curve, this vector gets changed, because when someone is over here, let's say point A, the vector from the origin will be here, and as one moves along, the vector will change as well. And let's say this is point B, this can be point C, this can be point D, and if you recall, this r vector is just the radius vector or the radial vector. That means from the origin to the position that you are interested in. So that's why I told you that this curve can be parameterized as r of u. So this r of u will actually mean our curve. So now what we're going to do is that we're going to use this relation that we just saw over here. This will be pretty helpful. And now, since we are considering the curve, this dr will actually mean a change in the curve. That means if someone starts from, let's say, point B and goes to a very tiny distance on the curve, the displacement between these 2 points will be denoted by dr. Okay, so now let's use that relationship to our advantage. So using the relationship above, that is del phi dot dr is equals to d phi, we can write that this del phi by del u, that is, you are taking a differentiation, that is, you are differentiating the field with respect to the parameter, and if you do that, then this will be just del phi dot del r del u. Okay, so you might ask, why am I doing this, and how does this even make sense? Because we told you that phi is a function of x, y and z, right? So how can you differentiate with u? Note that since this curve has a parameter u, and this curve is also in this 3D space, so our curve will actually be a function of x, y and z. But since we are telling that we can parameterize the curve with only one parameter, and that is u, so instead of writing this x, y and z, what we're going to do is that we're going to write r of x of u, y of u, z of u. A very similar example, or a very simple example, is the circle. If you draw a circle, obviously this is a function of x and y, but you can introduce a theta parameter and you can express x in terms of theta and y in terms of theta, right? Obviously same thing goes for a sphere as well. So that's the motivation behind taking this derivative over here. Now we have something like this over here, and this is a quantity of interest, that is this dr by du. Since this r is actually a direction, that means it points us from the origin to the point of interest on the curve, and we are differentiating with respect to the parameter. So this is the guy we call the directional derivative. Okay, and now we are also saying that the field that was defined in this 3D space, inside which there is this curve, it also has some gradient. It's containing the gradient. So now comes the interesting part about this field itself. So we are writing this d phi du is equals to del phi, and one more thing to note is that this u, that is the parameter, is most often taken as the arc length. So in those times, people, instead of writing u, write s, but it doesn't matter. So here we have this directional derivative thing, and let's call this a hat. This is the thing we are calling a hat, and it can be reduced to unity, that is the norm of this thing can be reduced to unity, or let's say the dot product of this thing with itself can be taken to unity. So that's why I'm using this hat over here. So finally, using this unit vector and this dot product, if you evaluate it, this will give us the modulus of the gradient, the modulus of a hat, and cosine theta. And since a hat is unity, we can write it as gradient of phi of cosine theta. Sorry, I wrote phi instead of theta. So theta, like this. So now you have something as d phi du as gradient of phi, that is its modulus, and cosine theta. So what does this mean? It looks like some equation and it doesn't have any meaning, but indeed it has a very important meaning, because if you zoom in the curve, so now I'm not drawing the coordinate axes, just drawing a portion of the curve, and in this curve you can see that the direction of the gradient will be something like this. This is the direction of the gradient, okay? And since the a hat, that means the tangent, because this is like a tangent thing, this dr by du or a hat, this is like a tangent thing. So this thing will have a direction like this. Obviously it doesn't look like a tangent because the drawing is not very smooth. So, and this is our angle, so this is our a hat. And from this figure we can easily see that this d phi by du, that is the rate of change of the field itself, is along the direction of a hat. And this means that the gradient is actually the direction in which the curve or the function, that means the function phi, changes more faster. This might be a bit confusing at first, but if you just look at this drawing, you can easily see that this gradient of phi will actually give you the direction in which this function phi is moving faster or slower. That is, it's the direction in which way the function is changing most rapidly. So now you might ask, why will I even bother with these things? Well, because let's say your room has some temperature and you want to see in which way the temperature is changing very fastly. That is, if you move a little bit, the temperature is changing in a very rapid manner. So in that case, if you can represent the temperature of that room with respect to function x, y, and z, and you can take the gradient of it, and finally you can conclude in which direction the temperature is either rising or falling very fast. You can also use this kind of techniques into geographical studies. For example, if you are on a mountain and you can see that there are 3 or 4 ways to go downhill, and you cannot decide that which way you should go, and if some magician comes and gives you a function that represents the surface of the mountain, then you can find the gradient and find the most steepest slope, because in the steepest slope the function will change very rapidly. It will either go uphill or downhill, and you can easily find your way from there. So these are pretty a bit abstract mathematics, but you can obviously find the geometrical meanings of this kind of things. So this will be it for today, and I'll see you guys on the next lecture. Thank you.